Hello guys, so today we are starting a greedy part from this sheet on neetcode.io. So we will be trying to solve these greedy problems. So I think this is the last major topic. After that we have some mixed topics like intervals, math and geometry and bit manipulation. Okay, so let's start. So let's start with the jump game. Okay. Okay, so the problem says you are given an integer array nums. You are initially positioned at array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index or false otherwise. Okay, means you are given an integer array nums, and we are initially positioned at the first index. Okay, and each element in the array represent your maximum jump length at that position. Okay, return true if you can reach the last index or false otherwise. Okay, so in this example, initially suppose we are at 2, so jump one step from 0th index to. Okay, so from here we can jump two steps, means we can jump to this position and this position. Okay, so what we are doing is we are deciding to jump on this position. Okay, because we can jump two steps, so we are only jumping for one step. Okay, from here we can jump three steps: one, two, and three. Okay, so we can reach the last index. That's why we are returning true. Let's say we are at this index 3. So let's see, we can jump from here to here, one jump of length 1, uh, and then to here the jump of length 2, then directly or can here. Okay, the jump of length 3. Suppose we jump length of 3, that means we reach here, and from here we cannot jump because the maximum length is 0. So from here we cannot reach the end. Suppose we jump from 3 to 1. Okay, so from 1 we can only jump a single step, so we reach here, and from here as we know we can't reach the end. From 3, suppose we jump at 2 position, from 2 we can jump here and here. Okay, so eventually we cannot jump to the last position, so that's why we are returning false. Okay, so let's say we have this example. So we are at 2 position, so maximum jump we can take is means from here maximum position we can reach is, so basically this is maximum position from this index, from 0th index we can reach is the current position 0, and plus 2 jumps we can take, so we can go to the 2 position. From here we can go till second position. Okay, let's say from here we go to position 3. means we go to the index 1. Okay, so from index 1 we are at index 1. So the maximum position we can reach from the index 1 is the current index which we are at 1 and plus the value of the maximum jump. So we can go 1 plus 4. For here let's say 0 plus 2. So this is the max position 1 3, sorry. So means we can so basically n here is the length here is 0 1 2 3 4. So our target is 0 1 2 3 4. Target is 4. So basically we can from this particular index we can reach the end, let's say. Okay, so the maximum position basically we can, basically our maximum position is equal or greater than the target. So from this index we can reach the maximum position. Okay, so suppose we don't do this, we let's say try to go from 2 to 3, 2 to this 2 to 1. Okay, so from this one which is at index 0 1 2, second index, the max position we can reach is currently we are at second position, second index, and the value 1. So we can go to the index 3. Okay, so we can basically reach this index. Okay, so from this one then we can go to index, this value 1 which is at index 3. And from this index 3, let's say we are at index 3 and we can jump one position ahead, so we can reach the 4 from here itself. So basically one way is this and one way is this. So what that means is uh, standing at a current position we can decide the maximum position in future we can reach. Okay, from the current position we can decide the maximum position we can reach. So this will be means from in this particular example we can reach the maximum position, means the last index, into two ways. So we can reach the end index. Let's say if we are considering this example, so target will be same, and initially we are at let's say we are at index 0. So the max position we can reach from index 0 is 0 plus 3, which is 3. Okay, so means we can go to third index, means we means third index, this particular index is accessible to us, means whatever we do this particular index is accessible to us. Okay, so then we say can we go to the index first? Yes, we can go to the index first because we can go to the max position till 3, so we can of course go to the one position. So from one position our max position we can reach is the current position plus the current value 2, means from first position also still our maximum position remains 3, means still we can go to the maximum position 3. So now can we go to the index 2? Yes, as we can go to maximum index 3, so we can go to index 2 also. So from 2 uh, index 2 is having value 1. So from index 2, 2 plus 1, we can go to this particular index, which is still 3. So still we can go to the index 3, which is the maximum value. So now we have index 3. So can we go to index 3? Means is index 3 accessible? Yes, it's accessible because the maximum position which we can go from the previous jumps is 3. So we can of course go to the index 3. So next position here is current index 3 and the value 0. So means the next position is 3. So now we see the index is 4. So can we go to the index 4? No, we cannot go to the index 4 because the maximum position is not updated. It's still 3, so we cannot go to the position 4. I think this is the greedy way to do it. So what we can do is we can first create a length, nums dot length. Okay, and initially the max position will be a 0, means we can start from, as per question, we can start from the first index. So that means the 0 means the zeroth position is accessible to us. Okay. Okay, so let's start from int I equals to 0, means we start from 0th index. Okay, so from 0th index the max position we can reach is okay, first we will see, means if our let's say max position, if it's greater than or equal to I, then only we can uh, go to the, means then means that means the current index is accessible to us. Okay, if it's accessible to us, so we will optimize our max position, means we see if we can from the current index go a further position, means the current index plus the value of the current index. If it's greater than the maximum position we can go, so we can update our maximum position. Okay, and at the end we can also check if our maximum position becomes greater than equal to n minus 1, that means we can go to the last index, so we can return true, and otherwise we cannot go at the end, we don't have any possibility of going, so we can return false. Okay, int n is equals to nums dot length, max position is 0, we can go only go to the ith position. If it's greater, okay, then only we will be updating maximum position. Okay, we can also say that if our maximum position is smaller than the ith index, in that case also we can return false, means we can do reverse of it also. Means something like means if the current position is not accessible to us, we can return false, and otherwise all the positions will be accessible to us till the this loop runs, so we can return true at the end also. Mm, okay. Hmm. How can we zoom something? Okay, let's run this. Okay. Okay, so this was the logic to it. Okay, let's try jump game 2. Okay, jump game 2 says you are given a zero indexed array of integer nums of length n. You are initially positioned at nums 0, means similar to the previous question. We are at starting from this position, starting position 0th index, and each element nums of I represents the maximum length of a word jump. Sorry, a forward jump. Okay, same as the previous question. In other words, if you are at nums I, you can jump to any nums I plus j. Okay, okay. J is in between, and I plus j is smaller than n. Return the minimum number of jumps to reach nums of n minus 1. The test cases are generated such that you can reach nums of n minus 1. I think question is saying that we can jump from this position to this position, and this position means we can jump maximum of two length, and we need to return the maximum sorry minimum number of jumps we can take to reach the n minus 1th index. We need to find minimum number of jumps to reach the last index. But what means each element nums I represent the maximum forward jump from index I. Okay. In other words, if you are at nums I, you can jump to any. Okay, we can jump to this particular index where okay, I think the description is confusing, means this part is confusing. Means the question is trying to say we can jump from nums I to the next positions such that means this is the j is the length of our jump. Okay, suppose we are at index 0, means I is 0, and we can jump 2. So the question is saying we can jump to 0 plus 2th positions at max. Here they haven't mentioned that. Okay, so they mentioned here that j is can be smaller than equal to 0. Okay, so the question is same as the previous one jump came, but here we need to find that can we means we can go to the end position, means it's given that we can there is a solution that we can reach to the end of the array, but we need to find that minimum number of jumps in which we can reach. Okay, so here we have this array, so we have started from 2, so from 2 we can jump to 3, and from 3 means this is from jumping from 2 to 3 means we are taking a length of 1 unit, and from here we can directly jump to this position, so that's why we are returning 2. Means we require two jumps, one from 2 to 3, then 3 to 4 directly, and we need to find minimum number of jumps. In this example also the minimum number of jumps is 2. Still we can jump from 2 to 3 and 3 to the last position. Means from 3 we can take a, from here we can jump a maximum length which is 3, 1, 2 and 3. Still the answer will be 2. Okay, so I think we, the difference is only that we need to find the minimum number of jumps. Means it's something like means from this particular element which is starting element we can reach to the end element in many ways, but we need to find the way which take the minimum number of let's say jumps. And if we can consider a jump as a edge, so we can implement the, let's say we can implement a logic or like which we use in BFS or dicastra, like we can prioritize the minimum jumps first. The, okay, so what I'm trying to say is in the previous example, so we were at a zeroth index. So okay, so this was that example where we were not able to reach the end, so we cannot consider this example. So what I'm saying is let's say I take this code and I paste it here. I think it's not pasted correctly. Okay, we have pasted this as extra. We can't return something. So what we were doing is we have implemented something like this. If our maximum position reaches at the end, we can return true from there itself. Otherwise, we were returning false. Okay. Okay. Okay, let's say we put our jumps in priority queue, and we prioritize queue based on the number of jumps. So initially we will pop out elements on with the less number of jumps, and if any of the element along with the number of jump we can store let's say the maximum position we can reach. And if the first very first element which we pop out from the priority queue, if it reaches the means the end of the array, we can say that this is the minimum number of jump we can reach. Means we can use a priority queue. uh, Priority queue of, let's say, this variable pq, new priority queue. And we can suppose we have this array of size 2. At zeroth index we will store the number of jumps. So we need to prioritize it based on the zeroth index. Zeroth index, and means uh, a b, and we need to prioritize it based on the zeroth index, keeping the smaller values. Means we are creating min priority queue basically based on the number of jumps. And let's say we are at position, initially we put something like the value 0. Initially we have 0 jumps, and we have 0 maximum position we can reach. Okay, so now here what we are doing, we are checking if our maximum position is greater than equal to I. So in this particular example it will be always greater than or equal, because we can reach the end of the array. So what we can take is, we can take the maximum position. Means maximum position will be current position, and the uh, value we are adding, means the current value at the ith, means the index plus the value, current value, the number of jumps we can take. So this is the number of the jumps we can take. Okay. Suppose we pop out from our priority queue. So initially we have 0 jumps and 0th position. Okay, means int, we pop out from our priority queue, and we check if our this value, means the 1th value, which where we will be storing the maximum position, if it becomes greater than or equal to the n minus 1th index, if we reach the end, so we can return the current number of jumps, because we are storing based on the minimum number of jumps in the priority queue. So we can return the jumps. Okay, otherwise we will calculate the maximum position we can reach from the current position. Maximum position we can reach, and we can put into our priority queue the number of jumps plus 1. Okay, and the maximum position we can go, that will be maximum position. Okay, can we try run it so that we can check if it's working? Let's say we have this array. Okay, so initially our priority queue, so let's say this is our priority queue, so priority queue will have 0 and 0. Now we start from 0th index, so we are here, I is equals to 0. We pop out this pair, and okay, so n here is 0 1 2 3 4, and here is 4, and pq priority queue is this. Okay, so can we reach the end position? We will pop out this element and check its maximum position. 0 is 0 greater than equal to n minus 1, so n is 5. Okay, so no, it's not greater, so we will calculate the maximum position, which will be I plus value at the ith index 2. Then we will what we will do, we will put in pq, so we have popped out this pair and we are putting one jump we need to take, and means we are increasing the jump and the maximum position to 2. Okay, then we go to the one index and we pop out this pair from the priority queue, and we see if max position is greater than this particular part. No, it's not greater, so we will calculate the max position. Okay, we can't, we means from here we are calculating a jump, which is the zero jump, and we need to jump here. Okay, let's say we pop out this value and this is not greater from this position, maximum position. Means from this two in one jump we can go here and here, means this two values should be stored with the, go to the maximum position of 2. Okay, we, let's say we have a 0 here, let's say, and this is minus 1. Okay, so we can reach here, maximum position is 0, and from maximum position we can go to these two positions, means we can go to the 1th position in one jump. We can go to this position, and also in one jump we can go to this position. Means in one jump we can go to the maximum of position 2. Okay, In one jump, we can go to the maximum position of 2. Then we reach the 1 here. Then we pop out this element, and this is not equal to this. Okay. Then from this one, we can go to the maximum position of 4. Means we can, from this one, we can go to the maximum position. In second jump, we can go to the maximum position of 4. Okay. Maximum position of 4 from here. And then we reach this index, and from this index, index number 2, we can, we will pop out this particular uh, part, and we see that okay, so till index we can how many positions we can reach, we need to find. Okay, means till what index, till a index we need a minimum index we can reach, minimum jumps we can reach till a index. So initially 0 0, let's see. So initially 0 0, then we put 1 and 2. Okay, maximum position 1 and 2. Then we come here. Here we see maximum position is 2, which is not greater. We take maximum, which is 3 plus nums of 5, which is 4. Jump, we will increase a jump. We need to take a more jump. Then we reach here. Then from here, then we reach here, and we see if we can reach the end index before coming to this position itself, which we can. Means this particular example will run. Let's see if this works. So initially we are at 0 0. Okay. Then we are at 0th index. From 0th index we can go to the maximum position 1 and 2 in one jump. Okay, maximum position here we can go. Then we reach here. Let's say we start from here, and we pop out this particular element. Then we can go to the position 4 in the 2 jumps. Then we reach here. So before reaching here, it will also give us true. So these two examples will run, will work, I think. Let's see. Okay, these two examples are working. Can we think of any other example? Mhm. If we have 2 here, then can we reach at the end? Means we can start from here, we can go here and here. Means maximum position of this. Then From here we can go maximum position of this. Okay. Okay. Okay, let's run for this example. So initially we are at this position 0 and 0. So from 0 we can go to the maximum position of 2 with one jump. Hmm, no, it's not zooming in. Okay. Then from this one we can go to, means this position we can go to the maximum of this position plus 1 plus 2, which is 3. Okay, we can reach here, means we can in two jumps reach 3. Okay, then we pop out 2 and we are at here, we are here. Then from here can we reach? Okay, so from here we cannot reach anywhere. Okay, so this example will not work because we will while standing here we will pop out the this value. Okay, so this will not gonna work. We put 2 this will return -1 or 4 or 3. Okay, 3. Let's while the queue is not empty, we poll and we check if we can go. Otherwise, we can go from okay, now we don't have index here. So we also need the index. Like we can go from position, which is our current position is I plus 1, j smaller than equal to I plus nums of I j plus plus. Then we can go to position. These positions we can go. If it's 0, we cannot go anywhere. But this count will increase, and at eventually we will reach a position. Okay, can we do like this? Eventually we reach this position. Okay, let's see. Okay, so what I can do is initially I am at zeroth index. From that zeroth index, I can go to that index plus the value at the nums array. Okay, so I can start from J, means I can go to this position, and after increasing a jump. I think this should work. PQ is empty. PQ is not empty. Okay, okay. So if I cannot find symbol I, okay, so that means not I. Current index is this 1. Okay, this is the index, and if the index reaches greater, then we will not reach this condition. So that will not give us the error array of out of bound. Okay, it's working. Let's see if it gets submitted. It's giving TLE. Means this solution's logic is correct, but it's giving TLE. Means this part is giving TLE. If the jumps are not equal, then we will be prioritizing based on the. I think we have extra column parentheses. Okay, let's see if this works. Okay, it's still going to. Okay. Okay. Is D is the best place to jump from A to D at max. Assume you can jump from A to D at max. Okay. And you came to D. At D, you are thinking to jump further right, but then some question came to your mind. Is D is the best place to jump to further right? Okay. What if B was having better jump beyond D in the right side? What if C does even better? So basically, we have three choices: B, C, D. Okay, so these are the choices which we have in our solution. Assuming the fact that we already jumped from A, we are not sure yet. Not no need also. We just need count. So we keep in so we will keep maintaining maximum possible jump provided by B, C, and D and choose the best one. Okay, we can go from. So we keep maintaining maximum possible jump provided by BCD. BCD becomes kind of similar in the terms of jumping beyond D. We just need to choose the best jump at D. BCD becomes kind of similar in the terms of jumping beyond D. I don't know what he's saying, but our battery is not empty. Choose the best maximum possible jump. Okay. So current index is this, and from current index we can go to this value, current of j. Sorry, what I'm doing, nums of j. So this is the max jump. If we are here, when we are considering max jump from this, but we are not considering the previous values. What we do, this will also fail a test case. Let's see the TLE solution. Okay, so it's saying is maybe our solution. Sorry. That we need a queue only. Okay, if we take a queue only and to queue dot add, we have added this element. Do we have all positive values? Okay, we have all values as positive. So we can make a nums of, this is the number of jump, this is the index, current of 1 equal to -1 after calculating this value. Means this is the current index we are at and this is the value at that index, so we can jump these jumps. And then what we are doing, we are making this, marking this particular index as -1, and we are starting from this index and we are going till the max index this. And we will only add a if nums of j is not -1. I think that's the question asking. Syntax error. Hmm. Okay, this was the syntax error. Uh, this is the syntax error. Okay, starting from this value, we can go to this value. Closing due to redundant operation per name. No boundary check in for loop. Current means okay. Max index can be out of bounds. Uh, Hello. Mm-hmm. Okay, current position plus one. Number of jumps is zero. This is the current index. This is the jumps. Max index we can go. This plus this. Okay. If a value is not visited, okay, marking true it here itself that we have visited it here itself. Okay. Okay. So we are using a visited array. Can we skip using visited array? Means I'm using the current array, means this array itself as the visited array. Okay, we cannot use because we need to modify this approach, means we are marking true after popping out from the priority queue, but we need to mark it before adding to the priority queue, which is here. Means we need to mark it here as the visited. If we mark here it as the visited, then the problem is we can't access this particular index. That will be -1. Okay, so we need a separate visited array. Okay. We can mark it as visited as here. Okay. And then we can mark it visited here also. Okay. Okay, this is the what is the time complexity? Hello. बैंड चो बना के कौन देवे मन